Sorry about that. I got distracted. I just was about to say it looks like I can take the second derivative pretty easily, and I'm going to end up with 12x squared plus 6x minus 6. And I can factor a 6 out pretty quickly. This is going to be 2x squared plus x minus 1. Now I have taken a moment and I factored it your guys' way. There it is, the big X. So you could pause it and write it down, make sense of it. But I'm going to go in here and I'm going to just write down this piece and this piece right here, which is 2x minus 1 and x plus 1, because that's what it factors into. So I have 6 times 2x minus 1 times x plus 1. Here we go. I set that equal to 0. I'm going to solve. This little piece gives me a 1/2, and this little piece gives me a -1. And I am now declaring that these are my possible points of inflection. Okay, possible points of inflection. It's like candidates. It's like the candidates test for the critical numbers for the first derivative test. And in fact, it looks very similar because I make a number line. And then I'm going to throw up the second derivative symbol here to let you know that's what I'm testing. And I'm testing this -1 and I'm testing this 1/2. And in here now I have to be very careful. I want to make sure that I think about what happens if I plug in numbers that are in between my possible points of inflection. So you know how I like 10s and 0s. Looks like I can test those things pretty easily, so I will. So I'm going to think about if I throw in a -10 here, this number is going to be negative. If I throw in a -10 here, this number will also be negative. And so I get a positive there because a negative times a negative is a positive. If I check 0, then what I get is -1, right? And if I plug in 0, what I get is +1, right? So a negative times a positive makes this negative. And then if I plug in 10, I get 2 times 10, that's positive 20, minus 1 is positive 19, so this is positive. And if I throw in a 10 here, then what I get is also a positive. Positive times a positive is a positive. All right, yay. So it looks to me like what I can see here is because my original function is a nice, well-behaved polynomial. Stuff I know about polynomials, quartics, is that they have a tendency to look just like a quadratic. They might be a little bit flatter here than a quadratic it would be, but it grows super fast, right? It grows super fast because anytime you take something to the 4th power, it's going to grow super fast. But what I also know about a quartic is that it could have as many as 4 roots. And those roots could be located like, one here, one here, one here, one here. And how does it get 4 roots? Well, it must go down and then go up again and then go down and then go up again. So there's this little moment where you might see on a graph that it's concave down, and then that you see that it's concave up and concave up. And that's what I think I have going on here is I have concave up, and then I have concave down, and then I have concave up. So if we're discussing the concavity, I'm going to say that it is concave up from -infinity up to -1. And again, from 1/2 all the way up to positive infinity. And I like to put an and sign in between. Okay, now for concave down, it's just that little piece in the middle from -1 to 1/2. That's going to give me my concave down part. And let's double check this one more time. Looking at points of inflection, I know I can find tangent lines at the points where I think I have inflections, and I know that polynomials are well behaved, so I'm not having any problems finding derivatives, which is why I know that the tangent line exists. And then I'm saying for sure I noticed where it changed concavity at that point. So if you're thinking about where those points of inflection are, they are going to be right there and right there. And that would be my tangent, and that would be my tangent. Those are all very easy to find, very well defined. So I'm going to say that my points of inflection, I have just confirmed, are 1/2 and -1. And sometimes, you know, a little OCD here. Let me put the -1 and then the 1/2. Okay. Oops, I did forget to put down x equals. Okay. So now we've got that problem all sorted out. I'd like to take a look at number 6, and I'm so grateful because I noticed that the function is here and the second derivative is here. So I don't have to actually take a derivative. It's been taken for you. It says list the intervals where the graph of f is concave up and concave down and list those points of inflection. And I'm thinking about the original function, and right away I'm wanting to note that the domain, I can tell, is that x cannot equal 2 or -2, because if I do that I have division by 0, and that's bad. And I notice that condition remains in the second derivative. So my second derivative cannot equal 2 or -2. Now those are not possible points of inflection. They're just not in the domain of my second derivative. And it's important to note because concavity can change there, even though it's not a point of inflection. Okay, and so I want to take a look. Well, it can change around there. Think about it being asymptotic. If it's asymptotic at -2 and then at +2, you could get a function that looks something like this, right? So I have concave up here, I have concave down there, I have concave up there, or various versions of that. I could also have it being asymptotic, you know, in a different way, or say it's going to go up like this and then it's going to go over like that, and you know, who knows what goes on in between. So these are why I'm saying I want to take a look at 2 and -2. And I also know one other thing, which is that if I try to set this equal to 0 and solve, I actually don't have a way to get it to be equal to 0. Okay, I definitely know that if I set the denominator equal to 0, that's when I find these 2 points. But if I try to find a number that when I square it, and then I take it and multiply it by 3, and then I add 4 to it, and then I multiply by 10, there's literally no way that that same squared number will be exactly the same as if I minus 4 from it and then cube it. Okay, so just eyeballing it, I could tell that f double prime is never equal to 0. So that's why I'm pretty confident that there's no points of inflection here. So instead, I'm just going to use my double number line, my double derivative number line, and I'm going to put in my -2 and my +2, and I'm just going to check to see what am I getting out of this, you know, derivative when I plug in numbers that are around there. And so I do like tens, and so I might test -10. And if I plug in a negative here, I'm going to get a positive, and then I got a 3, and then I got a 4, and then I got a 10. And so it turns out this is a positive. And hey, down here, I've got 10, which is sufficiently large enough to overwhelm that -4. And so I also have a positive here. So that means this section is positive. All right, so what if I threw in a 0? So if I throw in a 0, this whole piece disappears, and I have 4 times 10, which is a positive number. This whole piece disappears, and it turns out on bottom that -4 being cubed, well, it's -64. Boom, that makes it negative. All right, and then I feel very familiar with what happens when I multiply by -10, and it turns out it's exactly the same as what happens if I have a positive 10, because I'm squaring it. So I square it, I get a bunch of positives up here, I square it, this is definitely bigger than that, so it's definitely positive here. So as far as points of inflection go, because it's never equal to 0, I'm going to say there are none. Okay, but concave up, I can confirm that it is going to be -infinity all the way up to -2, and it is also going to be at 2 all the way up to infinity, and then concave down will be from -2 up to 2. And I highly encourage you to take a look at that graph and confirm that visually on Desmos. All right, so